Hello everyone, I am Hiralal. I'm senior data scientist based out of Hyderabad. In this series, we will be focusing on what is vector database and we will be building it from scratch in this series. So let's start with what is vector database. And in this episode, you will learn what will be your complete journey of building your vector databases from scratch. What is the problem with existing keyword databases? The way to search, there are two ways. What is a vector? How we move from two dimension to multi-dimension vectors? How a vector database works? And when to use what type of database? And then at the end we will see like vector encoding or embedding, what does it mean. So our complete journey will be distributed among 13 episodes. In the first 3 episodes, we will go into vector, distance matrix and cosine similarity. In the next 4 to 6 2 episodes, we will looking into the embeddings, semantic search and filtering. In the episode 7, we will see what is the problem with our database and how it fails on the scale. Then we will look into episode 8 and 9. Those are related to the approximate nearest neighbor algorithms. Then we will have a production level setup where we will use the FAS with plus our mini vector database. And at the last final episode, we will use REST API to serve this our mini vector database for the other applications. So the problem with keyword databases is, let's say if user is searching for the quick healthy lunch ideas and our database has an article which says great match but which is missed because our title was 15-minute quinoa bowl, no keyword overlap, not found. So how we will search with the traditional database? We will write a query which is select start from recipes where title like healthy. So it will miss quinoa bowl because quinoa bowl's title does not have healthy word in it. So to overcome this sort of limitations, we will go to the other solutions of the vector databases. So there are two ways to search. One is card catalog. Just assume this as an library example where you can have exact title lookup. You can find books by author or you can find via exact subject headings which will match the keywords and you can find the book. But assume there is a smart librarian. You just give your natural language requirement to that librarian. Librarian will understand your requirement and comprehend it and then give you results. So it will understand meaning, it will find the relevant concepts and handles the synonyms as well, and that is called matches meaning. So traditional databases with the tables, they will match words, but this will match the meanings. So now what is a vector? Vector is just list of numbers. Each number represents a dimension of meaning. And let's take an example of 2D database. So on one axis we are taking energy, one axis we are taking happiness. And let's say we are representing four words, which is excited, calm, sad and angry. Excited means high energy, high happiness. Similarly, calm, high happiness, low energy, or like slightly lesser than the excited. Sad, low on both, and angry, high energy, low happiness. Similar meaning, close together. If let's say the new word is joyful, then joyful is related to excited and those are like close together. Different meaning, far apart. So sad and excited are far apart, so they mean differently. So from 2D to 384 dimension, like what we saw in example, that is same. Our example was just 2 dimension. You can represent the same number with the 3 dimension. But in the real life, our example would be more complex or the more meaning. Then we will have the real dimension, which can be 384 dimension or it can be more than that as well. But we cannot visualize 384 dimensions, but the math works the same way. Similar things end up close together, different things end up far. How a vector database works? So it works in 3 steps. Very first, we used to call it embedding. You will have your input text, image, audio, or any form of the raw data that will pass to some ML model or the encoder model, which will give you a vector as an output. Second, you will take those vectors along with some metadata and you will store them into some vector data store. That are we planning to build this piece. In the search, user will write a query. You will take that query, you will pass through same embedding model, create embedding out of it, and then you will find which documents are near to the user query. So meaning of life, let's say this is the user query, you will create embedding out of it and then find the closest stored documents. So embed, store, search, that's the entire architecture. When to use what? When to use traditional database SQL or when to use vector database. Exact matches, let's say if you're looking for some ID or some record, then you can use exact match or the SQL databases. If you're looking for range queries or aggregations or structured data with well-known schema, we should use SQL database. Uh, if we are looking for similar articles, products, images, or we are doing semantic question answering over the documents, or we are building recommendation engines, or if we are using this vector database for RAG and we want to feed this context of documents to the LLM, then vector database is the choice. But in most real applications, we use both SQL for structure and vector for meaning. Vector encodes meaning or it just embeds meaning. Proximity is similarity. If those are like close together, those are like really they will have the same meaning, or if they are far apart, then we will say they have different meanings. So let's walk you through a code example. So we will demonstrating similar things will have the similar semantic vectors, and different things will have different vectors, and the distance would be far. So similar concepts, let's say cat and dog will have the similar embeddings, car and truck will have the different embedding. And between cat and dog, we will have the smaller distances, and between car and dog, we will have the larger distances. So dissimilar, like animal versus vehicles will have the larger distances, but between the animals and between the vehicles will have the shorter distances. So import NumPy as NP. NumPy is a library to work with vectors in Python. Next, we are defining Euclidean distance. So this function takes a as an vector, b as an vector, and it will create Euclidean distance between these two vectors and returns it as a number. So in our main function, currently we are not creating vectors for these labels. So we are hard coding these vectors for the demonstration purpose, but going forward in the later episodes, we will have the real numbers. So cat, dog, car, truck, and bicycle. So then we will create a vector distances, which would be the pairwise Euclidean distance. It will be a matrix. Then we will calculate distances between the animals and animals to vehicles, which is expected to be far for animal to vehicle, and animal to animal or vehicle to vehicle would be expected to be close. So conclusion would be, if there are smaller distances, they mean similar, and if there are like larger distances, then they mean different. So let's run the example and see. So if you see, our 3D embedding vectors looks like something this. Then we are calculating pairwise Euclidean distance. This means we are calculating distance between cat and cat, so that is 0. Then we are calculating distance between dog and dog, so that is again 0. And if we calculate between bicycle and bicycle, that would be 0 only. So key comparison is, if we compare cat and dog, distance is 0.086. So that is animal to animal, and it's expected to be close. Same car and truck, distance is 0.12. It's again vehicle to vehicle, and this is expected to be close. But if we calculate between cat and car, the distance is 1.16, which is a bit greater than the what we saw in previous example that indicates animal versus vehicle, and this is expected to be far. Then we have the dog and truck. Similarly, distance is in 1.14. It's again animal versus vehicle, so this is again expected to be for. So conclusion is like cat to dog, a small distance, similar meaning. Car to truck, a small distance, similar meaning. But cat to car, larger distance, a different meaning. Vector databases exploit this property. Similar items live close together in vector space. So finding related items is just finding the nearby points. In the next episode, we will build our first vector data store in pure Python. Let's stay tuned. Thank you.